Students, in this video, we are going to continue with chapter 10, Light. Now, in the previous lecture, we have started what is refraction, what are the two laws of refraction, what is the cause of refraction. And we have also introduced in one of the laws, that is Snell's law of refraction, we have introduced one new term, refractive index of a medium with respect to another medium. In this lecture today, we are going to study what is relative refractive index, what is absolute refractive index, and different expressions that we can write for them. So let us first recall Snell's law of refraction, which gives us the definition of refractive index of a medium with respect to another medium. Since this is a definition I am saying for refractive index of a medium with respect to another medium, so indirectly it is a relative refractive index of a medium. Now let us see here, for a given pair of media and for a given color of light. In the bracket I have written frequency because different colors of light have different frequencies. So if I say red color has one frequency, yellow color has another frequency. Okay? For a given pair of media and for a given color of light, the ratio of sine of angle of incidence to the sine of angle of refraction is constant and is called as refractive index of second medium with respect to first medium. You might be thinking this is nothing but Snell's law of refraction. Yes, it is. Even for the definition of this refractive index of a medium with respect to another medium, we use the Snell's law of refraction only because that gives us this definition. Try to recall here, we have medium 1, medium 2. Here light is incident at the boundary separating the two media. So from the first medium, light is traveling, it strikes the boundary separating the two media and part of light enters into the second medium. We are not going to consider the reflection part now. So part of light which enters into the medium, it bends. Now in this case, I have shown that it is bending towards the normal. See, it has changed the path. Here it has bent towards the normal. Okay, and this bending of light, if we remember, is called as refraction of light. Here I is angle of incidence, angle between the incident ray and the normal at the point of incidence, and R represents here angle of refraction, that is angle between the refracted ray and the normal at the point of incidence, or we can say at the point of refraction, as both these points are the same. So mathematically we can write from here that N21, what is N21? Refractive index of second medium with respect to first medium is equal to sine of I divided by sine of R, because it is a ratio of sine of angle of incidence to the sine of angle of refraction. So this is relative refractive index of a medium, relative refractive index of medium 2. Why relative? Because it is with respect to this medium. It means if I change medium 1, okay, if I change it to some other medium, then this relative refractive index of medium 2 will change, because it changes when the first medium changes. And also if the color changes, then the value will again change. So when we keep the color fixed, when we keep the two media fixed, then refractive index of second medium with respect to first medium is constant. I have already told you before that sine of any angle is a trigonometric ratio and its value lies between that range is given there. It can be -1, +1, or in between any value it can take depending upon the value of this angle. And also remember, sine of any number is a pure number whose value lies in that range, and so it is a pure number means without any unit. So if this is without unit, this is without unit, we can say refractive index of a medium with respect to another medium is also unitless. It does not have a unit, or it is also a pure number. Now this is relative refractive index because we are defining it with respect to any medium. Now let us see what is absolute refractive index. Now we know the most common medium around us is air. And I have already told you when I introduce the chapter light, that speed of light is maximum in vacuum, that is 3 into 10 raised to 8 meter per second. In air it is slightly reduced. Again, for practical purposes, we consider the value to be same, 3 into 10 raised to 8 meter per second. So if I consider first medium to be air, then instead of saying that refractive index of medium 2 with respect to air, let us say second medium is glass, refractive index of glass with respect to air, I will say simply refractive index of glass or absolute refractive index of glass. If second medium is water and first is air, again I will call it refractive index of water instead of saying it refractive index of water with respect to air, I can simply say refractive index of water or absolute refractive index of water. So absolute refractive index or refractive index of a medium is the refractive index of a medium with respect to air, we can say. As we have seen before, that cause of refraction is what? What it is? Cause of refraction is change in speed of light when it enters from one medium into another medium. Because light has different speeds in different media, and so the bending takes place and thus the refraction takes place. So without proving here, we'll just take this formula for refractive index of second medium with respect to first medium. We'll assume that this can be taken as the ratio of speed of light in first medium to speed of light in second medium. As light travels in straight path, so speed is same as magnitude of velocity. So now I have one more definition for refractive index of second medium with respect to first medium. I can write it is a ratio of speed of light in first medium to speed of light in second medium. If I see this, then I can also write the different expression for absolute refractive index. How? Now instead of n to 1, I'll just write n. Here n represents what? Refractive index of any medium or absolute refractive index of a medium. This is equal to sin I upon sin r, same, but first medium is now air, and using this, here this is equal to, we know that first medium is air and speed of light in air is represented by small letter c, whose value is 3 into 10 raised to 8 meter per second. So in this case, instead of using V1 upon V2, I'll simply write C upon V. So N is equal to C upon V, where C is speed of light in vacuum, V is speed of light in that medium, about whose refractive index we are talking now. Now students, in your 9th class, you have started one formula which is valid for speed or velocity of a wave. That is, V is equal to F lambda, where V is speed of wave or magnitude of velocity of wave, F is frequency, and lambda represents wavelength of wave. Now just remember that light is also a kind of wave, and this formula is also valid for light. So here V represents speed of light, F frequency of light, and lambda wavelength of light. Now if you remember, in 9th class you have studied that whenever wave enters from one medium into another medium, its speed changes and wavelength also changes, but frequency remains constant. So if I ask you which physical quantity remains constant when wave travels from one medium into another medium? Frequency. Why? Because frequency does not depend upon the medium, it depends upon the source which produces the wave. So if we follow that, here when light enters from one medium into another medium, F remains constant and V and lambda, that is speed and wavelength, changes. So we can write, using this, we can write the formulae for speed of light in first medium and second medium. There, V1 is F lambda 1, V2 is F lambda 2. F is written same because F does not change when the medium changes. And when we take the ratios V1 upon V2, which is also equal to now F lambda 1 upon F lambda 2, FF gets cancelled and we are left with lambda 1 upon lambda 2. So if V1 upon V2 is lambda 1 upon lambda 2, then this N21 is also equal to lambda 1 upon lambda 2 because it is equal to V1 upon V2. Now here I have written mu21 This mu is a symbol used in many books or to represent relative refractive index, or when we simply write mu, it represents absolute refractive index. But let us use this will be simpler. Okay, so we can use either of these two symbols to represent refractive index. So now we have these expressions. Let us see if we can write any more expression for this refractive index. Now let us consider two different media and just call them medium 1 and medium 2. It's not first or second medium, two different media, medium 1 and medium 2. Then the refractive index of medium 1 can be written as C upon V1, where C is the speed of light in air or vacuum, divided by V1. V1 is the speed of light in medium 1. In the similar manner, refractive index of medium 2 can be written as C upon V2. And if I divide N2 by N1 and put these expressions there, I can see that C gets cancelled after I simplify it, and finally N2 upon N1 becomes V1 upon V2. So, but V1 upon V2 is what? N21. So, N21, now we have got one more expression for N21. N21, that is refractive index of medium 2 with respect to 1, is also equal to the ratio of absolute refractive index of medium 2 to the absolute refractive index of medium 1. I can avoid the term absolute and simply call it as refractive index of second medium with respect to first medium is the ratio of refractive index of second medium to refractive index of first medium. Now let us see the diagram here showing refraction. Let us call this as medium 1 and this as medium 2. An incident rays here, when it enters into the second medium, let it bend towards the normal. Now here, using Snell's law, N21 is sin I upon sin R. Okay, I don't think so you should have any problem in understanding this. Now we know that light follows the law of reversibility. It means what? If I reverse the direction of light, now light was moving in this direction initially, like this and this way. If I reverse the path, if I make these arrows in the downward direction, let the light travel in this direction now. Then when it enters into the second medium, it will follow the same path. It means I have to only reverse the arrows when I reverse the path of light. Let me not change the symbols for the angles there. And let me not change the medium. Let me call this incident medium to be medium 2 only, and the second medium actually to be medium 1 now in that case. So if I use Snell's law of refraction, refractive index of second medium with respect to first medium, there it will be N12 because our second medium is medium 1 and our first medium is medium 2. So refractive index of medium 1 with respect to 2 is equal to sine of angle of incidence. In that diagram, R is angle of incidence and I is angle of refraction. So I can write, using Snell's law, I can write N12 is equal to sine R upon sine I. Here N21 is sine I upon sine R. There N12 is sine R upon sine I. Both are reciprocal of each other. So I can write N21 is 1 upon N12 because they are reciprocal. So N21, I have got one more expression for this. N21 is equal to 1 upon N12, or refractive index of second medium with respect to first medium is the reciprocal of refractive index of first medium with respect to second medium. I hope you have understood these expressions very well. Now let us consider few simple examples of refraction. Now students, you must have seen, if you write anything on a piece of paper and place a glass slab over it, when you place the glass slab over it, you will see that the written letters appears to be raised. Okay. Now similar to that, if you see the swimming pool, we may feel that it is shallow, it is not very deep. Depth of water seems to be less. But actually when you step into the pool, you see that it is deeper than what you had imagined, what you had expected. Okay, so that is all because of refraction of light that takes place through the water. Similar expression, similar example I can consider here. If I have a vessel containing water, let us say this vessel is containing water and a coin is placed inside it at the bottom. Now, before I explain you this, let me remind you, in case of reflection we have seen, to get the image of a point, we were drawing two incident rays from A, and point where the rays meet or appear to meet after reflection used to be the image of A, and we denoted it by A dash. Similarly, in case of refraction, also image is formed, but it is formed due to refraction, not due to reflection. So here also we can take, to get the image of a point, we can choose two suitable rays coming from the point and get the point where they meet or appear to meet after refraction. And that point where the rays after refraction meet or appear to meet is called the image of that point. Okay? And also do remember, if I have this medium 1, medium 2 and this is actually normal, which should have been dotted line. So here I have drawn the incident ray on the normal only, means it is a case of normal incidence. So when the ray is incident normally and when it enters into the second medium, which should be transparent, then in this case there is no bending that takes place. It means the incident ray will travel along the same path, the refracted ray will travel along the same path without any bending. This is only when ray is incident normally. Okay? Now, let us consider this case. Here, a coin is placed at the bottom of water filled in this vessel. To get the image of this coin, I have chosen two rays coming from the center. To get the image of central point, let us say. Now, one ray I have taken this and the other ray is this. Now we are considering the beaker of containing water is placed in air. So when these two rays, which are looking, I have chosen symmetrical rays. Two rays coming from this point reach here, this boundary, this upper surface of the water. It is going to come out of water. It means it is going to change the medium. So obviously here refraction takes place. But how the ray should bend now? We know water is a denser medium compared to air. Then the ray should bend away from the normal. So at these 2 points, I have drawn two normals by using these two dotted lines. And I have shown that the ray is bending away from the normal. This ray is also bending away from the normal. Okay. So from here, I have chosen two incident rays and I have got two refracted rays. Since I have chosen symmetrical rays on either side, so I have shown symmetrical bending of these two refracted rays. Now they are not going to meet on this side, so I have produced them backward using these dotted lines. And I see that they meet at this point. Not meet actually, they appear to meet at this point. It means this is the image of this point of coin. So similarly, we can show that this coin appears to be here when we look from the sides. Okay, so this is the image of the coin that we see when we look from here. So in other words, we can say that the bottom of this vessel appears to be raised, as I have told you in case of swimming pool. Okay, so this depth, this is the real depth. Okay, and this depth, this is the distance from the image of the coin and to the upper surface. This is apparent depth. Now we know the cause of this example or this case is what? Refraction. So I can write one more expression for refractive index of this medium now, water. That is absolute refractive index of this medium is equal to real depth divided by apparent depth. Now I have drawn this one more diagram. Here I have chosen two rays from this point, coin. One I have chosen this, same as here, and the other I have chosen which is coming out normally, which is moving normally. So as I have seen here, the other ray which is incident normally at this boundary, it will go along the same path. So this is one of the refracted rays, this is other refracted ray. They are not going to meet this side. So this is already produced backward. So produce this backward, and again we get, this is a point where the rays appear to meet after refraction. So this is the image of this point, and hence we can draw the image of coin. So I have chosen, in these two diagrams, I have chosen two different rays to show that image is formed at the same place, whichever two rays we choose coming out from the coin. So we have now one more expression. This is for absolute refractive index of a medium, that is real depth upon apparent depth. I hope the different expressions for refractive index, they are clear to you. Now let us consider this last expression, okay, about refractive indices, and let us see how we can prove it. Although this is not directly included in your syllabus. See here, N12 into N21. N12 into N23 is equal to N13. Let me repeat it. N12, what it is? Refractive index of medium 1 with respect to medium 2. What is N23? Refractive index of medium 2 with respect to medium 1. When we multiply these two, N12 into N23, we can omit this 2 and write this is equal to N13. It means that is equal to refractive index of medium 1 with respect to medium 3. Let us see if we can prove it. Now we know this is the formula that we had derived earlier, that N21 is N2 upon N1. So using this, let me write what is N12. N12 is N1 upon N2. What is N23? N23 is N2 upon N3. I have just used that expression and written the formula for N12 and N23. Now multiply these two. So N12 into N23 is equal to, now multiply their right hand sides, N1 upon N2 into N2 upon N3. N2 gets cancelled. We are left with N1 upon N3. But we know that N1 upon N3 is N13. Therefore, N12 into N23 is N13. I hope the different expressions are clear to you. Although in your 10th class, basically you should know what is Snell's law of refraction. You should know the formula of relative refractive index from Snell's law. And you should know that it is also equal to real depth upon apparent depth, or N is equal to C upon P. The other expressions I have explained you, because if you give any entrance exam, they will be very useful for you. Okay, so please revise these topics well to have the better understanding. Thank you.